Starting with the broadest possible question, how do we get AI to generate a brand new image out of thin air? Imagine you have a massive collection of data, like pictures of teddy bears. Our goal is to start with something easy to create, like pure random noise, and somehow mold it into a real, high-quality image. To get from pure noise to a real image, you need a sense of direction. Enter the score. Think of the score as a compass in a dark forest. Mathematically, it is the gradient of the log of the probability distribution, but practically it simply points you in the direction where real data is more likely to exist. By following this compass, a technique called Langevin sampling allows the AI to take steps toward the actual images. But there is a huge catch. We don't actually know the true distribution of all real images. So our compass is basically broken from the start. The brilliant workaround for this is called denoising score matching. Instead of trying to map the unknown, we take our real images and intentionally add Gaussian noise to them. Why? Because the math for a Gaussian distribution is incredibly easy to compute. By optimizing our model to match the score of this intentionally noisy data, it acts as a perfect proxy for learning the true data distribution. This introduces a classic trade-off. If we add only a little bit of noise, our target remains accurate, but our compass won't work in areas of pure noise. If we add a lot of noise, our compass works everywhere, but the final target becomes distorted. The elegant solution is to use multiple levels of noise. You start generating your image using a massive amount of noise to point you roughly in the right direction. Like driving from Stanford to New York, then, as you get closer to the real image, you gradually reduce the noise level to refine the precise details. Going down another level, instead of using arbitrary discrete steps for this noise, researchers realized they could map this entire process using continuous time through stochastic differential equations. By treating the forward noising process as a continuous flowing mathematical equation, we can mathematically run it in reverse to generate clean images. We can even drop the random noise entirely during the reverse generation, creating a deterministic, highly efficient path called a probability flow ODE.